Good morning. Any questions before we dive into the material for this morning? Well, if there aren't any questions, let's get after it. We were looking at this problem in the textbook, practice problem 341, and I sent out an announcement yesterday, I think, that showed that there's some errors in this particular problem. So I wanted you to look at it and correct your book so you won't be misled if you are working through this one as a practice. So the problem starts off with this struct, and the struct has these fields in it. It has a pointer to a short, and we're in this problem dealing with a 64-bit computer. So that takes up 8 bytes for that address, right? And then we have this struct within a struct thing, just pretty much showing that you can do that is what's going on here. But you could have created a struct outside of this one and then used the name of that struct in here as the field rather than declaring it in here. But there's many different ways to achieve the same thing. So the name of this struct inside the test struct is S, and it in turn has two fields, X and Y. And then the last field in the struct test is a pointer to a test struct, one of these things itself, right? Which is a very common thing that you see in a record structure so that we can hook them together and have a linked list of records. This one points to the next one and it points to the next one. And then you can walk down the linked list of records and deal with them. So anyway, the declaration is showing it one structure can be embedded within another, just like you have arrays embedded within structures, and arrays can be embedded within arrays, and on and on and on. You know, any depth or combination of any of those things you want. And then they have this little sample code for a function that takes a pointer to one of these structs and then goes in and manipulates some stuff inside of that struct. And they want you to figure out what the missing C code is there. But first, they say, well, what are the offsets in bytes to the following fields within that structure? And there's a mistake in the answer they give you at the back of the chapter. We'll point that out. So P, the first field, is at offset 0. He's right at the beginning of the structure, right? So he's offset 0. S dot X, well, S is this inner struct, and the dot X is the field within that. But that would be laying right after this P, and P, the pointer, takes up 8 bytes. So the X field would start at offset 10, offset 8 from the beginning of the structure. The Y field comes right after the X, so that's 8 plus 2 for the short, so it would be at offset 10. And then here's the one they have a mistake in on the book. Next, they claim in the answer they show you at the back of the chapter that next is at offset 12. Well, that's not true. The largest alignment constraint we have in this structure is 8 for the pointer, the 2 pointers actually. So the whole structure has to start at an address divisible by 8. And then this pointer has to start at an address divisible by 8. which means that there would have to be 4 bytes of pad after these 2 shorts because you got 8, 10, 12. So he has to start at 16 to make sure he starts at an address divisible by 8. So there's 4 bytes of pad sitting after that Y, which means that the next field actually starts at 16, not 12 as they show in the book. Okay? So the next error they make in the back of the chapter is it says, how many total bytes does the structure require? Well, they claim it takes 20, but that's not true. It takes 24 because of the 4 bytes of pad after the end there. And to see that that is the actual truth, we can take this little program I wrote where I take their structure and I take this STINIT guy, ignore the commented out stuff right now. And I just put the code in there, and this is the solutions that will work out in a minute, but I put code in for their stuff, and then I ask it to print out the size of one of these structs for me, right? So if I do that, suppose I compile this, Alt-X in Emacs, type the word compile, hit return, and then the command, I had it there, shoot. The command I want to do for the compile is 3-4-1.c, right? So I want to compile that up. And it compiled it. So now I want to run it. So Alt exclamation point. And the command I want to run is a.out. Because I didn't tell it where to put it, and put it in a.out. So I run it, and it says the size of a test struct is 24. So you see they're lying in the back of the chapter there. So now we want to work the Control X1 to get that all the window back. Now I want to work the problem out, right? And see what the C code is that's missing here, which is really the meat of the exercise. So they say, okay, compile this STINIT function up and you get this stuff. Well, there's an error in there too. This isn't 12 here, it should be 16. And this instruction they have here is not exactly right. So if you compile it and you look at the code that comes out for our STINIT function, you actually get this stuff. It's pretty close to what they're showing, right? Well, we'll look at the differences. Rather than their move long word 8 past where RDI points into EAX, this one says move 0 word to long word, and it's taking the what the RDX points at and putting it in the EAX register. Well, the reason for that is, what is 8 past what RDI points at? Well, RDI points at the beginning of one of these structs. 8 past it jumps over that pointer and is the X field. The X field is a short. It's 2 bytes big, right? So we only want to pick up a word. So we're using this move 0 word to long word, which picks up a word pointed at by this address, the X value, puts it in the EAX register, and then zeroes out the high order bits of the EAX register to zeros. So we have that short sitting in the rightmost 16 bits of the EAX registers and 0 in the rest. The one they showed is move a long word. Well, that wouldn't be right? Because if you picked up a long word, that's 32 bits. What you would pick up is the X, which is 16 bits, plus the Y sitting next to it in memory, So you grab both of those and cram them in the EAX register. So that's not quite right what they're showing for the code, because you're dealing with a short, not a 32-bit long word, right? So we got this pick up a word and put it in a long word and zero out the rest of the long word, the EAX register. The next thing they got wrong is they show it now saying move this EAX register to 10 past what RDI points at. Well, 10 past what RDI points at is this Y field, which is in turn a short. And they're taking the 32-bit register and stuffing it into that location, which would stuff it into the Y, but it also would clobber the next 2 bytes after that, which in this case wouldn't hurt anything because it's just pad. But to do the real, do this, you would move a word 16 bits. We're dealing with shorts, right? And so you're moving what's in the, what's in the AX register, right? 16 bits, the rightmost part of this guy. And you're cramming that into 10 past the RDI, which is storing it in this short, those 2 bytes that the short occupies, get these 2 bytes pushed into them. So that's really the way to do that. What they're doing there wouldn't really hurt anything in this case, but it's not proper code. So what is all that doing? Well, it's picking up what is 8 past the beginning of the struct and stuffing it into what is 10 past. So it's putting the X thing into the Y. So what would the C code look like? It should look like this. ST, dereference it, get the S, get the X out of there, put it into the Y, right? We got passed in a pointer, one of these structs. So we have to dereference the pointer and select the field. So we're using our little arrow thing to do that. That combination, dereference the pointer, select the field in the record, right? And then it in turn is a struct, so we're selecting the field within it. So we're putting the X one into the Y one, right? Which is what that code does, right, in those first 2 statements. So now let's look at what the code does. I think they got this one right. Load effective address of 10 past the RDI and put it in the RAX. What is 10 past what RDI is pointing at? That would be this Y thing here is 10 past 8 plus 2, right? 10. But what we're getting is not the value of what sits there. We're getting the address of where that is, right? Load effective address of this location in memory, put it in RAX, and now move that RAX, a quad word, an address, right? 64 bits, into where the RDI points. Where does RDI point? It points at the beginning of the struct. So it's stuffing an address into this P thing, which makes sense because this says it's a pointer to a short, and we just picked up the address of this short and we stuffed it in there, right? So now this contains the address of the Y field in the structure, right? So that code there, those 2 instructions, is in C. Go to sts.y and give me that address of that location. Stuff that into stp, the p field, that pointer, right? Does that make sense? Okay. So it's a pointer to a short getting stuffed into something that's a pointer to a short, right? So the compiler's happy with that. So now we have the next statement says move quad word RDI, and RDI is the address of the beginning of the struct that was passed in to this guy, right? And put that at 16 bytes past where RDI points. So we go 16 bytes past, that's the next field. So it's putting the address that got passed in that points at the struct into this field called next, which is a pointer to a test struct. So that makes sense, right? We put a pointer to a test struct in the field, which is a pointer to a test struct. So that's doing this last piece, right? Take pointer that we got passed in and stuff that in the next field. So does everybody see how this C code is implemented by this assembly language code and vice versa? Any questions at all about that? Manipulating the fields in the structure, reaching in and grabbing things at a given offset from the beginning of the structure. So they had a few mistakes. They got the 12 instead of 16. The way they were manipulating this wasn't exactly kosher. They were grabbing 32 bits instead of 16. It mattered in the first one where you're stuffing it in there, right? Didn't matter in the second one. So make these corrections in the back of the chapter 3 solution to reflect that this should be 16, the length of the thing should be 24, and change the code that they show to reflect this business, not the stuff that they're showing. Okay? So any questions about this little thing that we have here? So this is the .s file, the assembly language, right? When you compile that and ask him to keep the assembly language for you. Let's look at some weird things that are going on with that. Let's go down to the main program and see what's happening down there in the main program. So the first thing you see in the main program is the little macro that's being called that we don't worry about now. I'll explain that to you later. And then you see this subtract 8 from the RSP. That's creating the activation record where the local variables of the main function will have a place to live, creating a chunk of space on the stack by moving the stack pointer down 8 locations. And those 8 locations will be what will be used for the local variables. So to create the activation record for the currently executing function, you simply subtract from the stack pointer, and then when you get ready to leave, you have to put it back where you found it, right? So that the guy that calls you, to do the return instruction, we got to get the stack pointer sitting right underneath where that return address is, right? So we got to put the stack pointer back. So that's just that's the normal sort of stuff you see for creating an activation record and then restoring it back, and then you do your return. And all these other little macros, these CFI call frame information macros, I'll explain later at some point to you. They aren't really needed. They're just in there for, if we're using the GDB debugger, there's some information being squirreled away here that the debugger uses. And it's also how the stack unwinding happens when you have exceptions and you have to peel things off the stack. But we'll worry about that later. Just ignore it. So the next thing you see is this business here, and that stuff is also something that I'll explain later. what's going on here. It has to do with a way that we do what we call putting canaries on the stack. So we'll get to that later. So the first thing that we're interested in here is this move the 1 into EDI, move 0 into EDX, and then it calls this little function printf chk. So it's not actually calling the printf function. He's calling kind of a cousin of the printf function. And that will become, maybe we'll talk about that at some point down the road. But in any event, that's how we're calling this thing to print out the stuff to printf. And what he's printing is this, here's the string, right, laying in memory. So when you want to, in assembly language, create a bunch of characters laying in memory, you can say, you can do it many different ways, but one way to do it is dot string. And that'll give you a C style ASCII Z string with these characters sitting in memory and then a 0 byte after it. Remember the 0 ASCII Z, 0 terminated ASCII string? That gives you that thing laying in memory like that. And so then the printf guy, or in this case his cousin, is going to look into that string and then print the junk out and then use the little formatting thing in conjunction with the other parameter that we're passing him, which is this number, which is just the number 24. All right. So what's weird about this? We do this little crud, don't worry about this move 0 to EX thing after you get back from the call. Then it's restoring the stack pointer back to where it is, and then it's returning. But what seems to be missing in this code here for main compared to what you see over here in the C code for main? What's missing? Anybody? Is anybody out there? Any wild guesses as to what we don't see in the assembly language and we do see in the C code? Come on, take a stab at it. Just make a guess. What don't you see? We don't see him ever calling our STInit function. And we don't see him setting up a parameter pass into it. We don't see him doing any of this assignment crud here, right? So what the heck happened? Well, the compiler optimized it out of existence. The compiler said, well, you got this variable R sitting here, right? You pass the address of that variable into this function you got up here. You munch around and do some things and change some values in this variable R. But then when you get back, you don't ever do anything with R. So what's the point of ever manipulating it if you're not ever going to do anything with it? So he just, boom, threw it away. Said, you don't need that code. Doesn't accomplish anything, right? So it optimized it out of existence. So how can we force the compiler to do this call? Well, I compiled it, if I remember right. Let's see. If I remember right, I think wrong computer. Get on Schofield here. I compiled the thing with a command that I think I said GCC -s, give me the assembly language, and optimize it level 1. 3-4.c. I think that was the compile command I used. So let's do a less on 3-4.1.s and see if that. So we're getting all the same stuff, and then down here in main, yeah. So that must have been kind of how I compiled that, right? You don't see the call exist anywhere. So if I go in and I say, okay, I want to compile the thing, but I want to optimize at level 0. I don't want to have any optimizations. And then I do the less on that. Well, first off, you see a whole bunch of weird stuff going on up in STinit now that we'll talk about in a second. We have the optimized version. And then down here in the main, all right, you have a bunch of stuff we didn't have before, but we still don't see any call. Oh, there it is. There's a call to the STinit, right? So we made the tell the compiler get dumber and don't do any of these funky optimizations. And so we actually called the thing, right? But we also got a bunch of other extraneous crud as a result in our STinit function of turning the optimization off. And so when we turn the optimization off, now it kind of looks like he's sort of halfway behaving like the 32-bit calling conventions. Rather than just getting the thing out of the RDI register, he's saving off the base pointer, putting RSP in the RBP, and then he's doing all this stuff. He's taking the I, which is where the parameter came in, right? And he's saving it at 8 below the base pointer. So that's, you know, what we call that um, red zone area, right? So he's saving off the parameter. And then when he gets ready to use it, he reaches into memory and he gets the dang thing and puts it in there. And then he does the instruction, you know. But this is accessing memory, that's accessing memory. So this is really slow and dumb, right? And then he's getting the thing again and putting it in EDX. And then he's, you know, he's getting the parameter, right? 8 past where that thing points. So this is all kind of nasty, unoptimized stuff compared to what we had before, but he did make the call. So how can we get him to emit code that doesn't have a lot of extraneous, worthless stuff in it, but also force him to make the call? Well, the way we can do that is by doing something in the function that gets called that will prevent him from being able to eliminate it. And so to do that, I'm going to uncomment this. Right. And here I'm going to declare a variable X inside of my function, and there I'm going to assign to it. But I'm going to put this little keyword here, volatile. So what volatile says to the compiler is say, hey, every time I touch this variable, you put code in that shoves that back to memory immediately. Don't do any funky register optimizations of leaving this in a register and not spilling it to memory unless you have to. Don't do any optimizations that would totally eliminate this assignment as unnecessary because I'm just assigning to a local variable and then I get back and it just disappears anyway. So I never used it after I assigned to it. So you would optimize that out of existence normally. The volatile says stuff that into memory. And the reason the volatile exists is think about if we had two threads running in the same address space, right? And one thread was looking into the memory of the other thread, waiting for some value like this to change. And then that would be his clue that he could go off and do something or whatever, right? So volatile exists for that kind of situation where you say, I'm forcing you to stuff this into memory, even though it doesn't look like it ever gets used for anything. So that that other thread will look in here and see that it changed and then he can do his thing. So that's the reason we have this volatile. But what I'm using it for is to hoodwink him into not optimizing the call out of existence, right? So uh, force him to not optimize the call away, and then I'll print out the value of the RSX field and the RSY field, right? When we get back from the function call up here, right? So let's compile that, and we'll compile it. Control XS to save it would be a good thing. And then now we'll compile it. And when we compile it, we'll do our, go ahead and knock yourself out, optimize it level 1. So now we see we get our cleaned up, sane code for the function. It's not doing a bunch of unnecessary crud and kind of got halfway the 32 style stuff and halfway the 64-bit style stuff. So it's just the stuff we went over before. Only now you see this take 7 and stuff it into 4 below where the stack pointer's pointing. That's this local variable, right? That's the space in the stack where that local variable lives. And then we get down to our main function, right? And we see, voila, he did make the call to STINIT. And so to make the call to STINIT, he had to provide the address of the R variable, our struct over here, and to get that put into the RDI register. So how did he do that? So he says, put a 1 in 8 past RSP. That's this code there, right? So the RSP is where the stack pointer is pointing, right? And that is the first local variable that we have in our activation frame, right? So the RSP is pointing at where this variable lives in memory. If we had another variable, he'd be below there or whatever, right? So we're getting that R, right? That address of the R, and we're putting 8 past that, which is the X field, right? It's 8 past where the beginning of that struct is, stuffing the 1 in, and then he's stuffing it into the Y, right? So we see that code happening now. So that gets in there. And he did that because he couldn't optimize that away, because now we're passing the address of that thing into this function. So he has to do that, right? So we're taking the address of where the R variable lives, putting it in RDI, which is how you pass the parameter, put it in, Diane silk dress thing. The first one's DI, right? And then we call the ST function. Now, when we get back, we want to print this junk out, right? And so he's going to have to print out the R.S.X and the R.S.Y. And so that's what that is. That's the 10 past the beginning of the thing is the Y, and 8 past it is the X, right? And then he's got this thing in here, which will explain what this program counter relative addressing stuff does later on. But he's just putting that into the second parameter that he's going to send off to the print thing, right? And he puts the other arguments into the print thing. So in any event, when we get back, we print those two things. And so if we run it, right, let's compile it, Alt X, up arrow, compile. Yep, that's what we want to compile. And let's go ahead and put our -O1 in so we get the same stuff we're looking at on the screen. And compiled it. So now we want to run it. Alt exclamation point to run a shell command. Up arrow, 8 on out. Runs it. So we get the size 24, and then we get back from the main from st call, and we print these two things out, and we've got the 1 in there and a 1 in y, right? So if we look at this thing, Control X1, make that the whole screen, right? Why do we have a 1 in the y? Well, remember we swapped the x into the y, right? So if we printed it out before the call, right? Control space to set the mark, down arrow to get the paste, Alt W to make a copy of it, go up here, Control Y to yank it, and now go up here and we'll say before in main before call to st in it, and we'll print the same junk out. It should have 1 and 2 in it, right? Control XS saves it, Alt X, up arrow, compile. That's what we want to compile. Hit the return, Alt exclamation point to run the shell command, and then up arrow, that's the shell command we want to run. So now we see the thing has the 1 and the 2 in it, but when we get back from the call, it has the 1 and the 1 because Control X1, the function actually clobbered the y with the value of x, right? We passed the address of the struct in. So we're actually manipulating this variable that lives in main, right? In his activation record on his chunk of the stack space that is his activation record. We're passing an address of that into this guy. He's reaching in and monkeying with that back in the caller's activation frame because we handed him the address, right? Everybody cool with this? What's going on, right? So I got 1 and 2 in it before the call. I got 1 and 1 in it after the call. And I forced him to actually not optimize the call away by doing this little trick here, saying that was volatile and then actually touching it. So he had no choice but to emit code for the call. So what do we learn? Well, we learned that if you compile this junk with no optimization, you get a bunch of extraneous crud where he's doing unnecessary things, saving off the parameters into an activation record slot and doing all kind of stuff. So if you don't want him doing silly things that might confuse you, why is he doing all this mess that he doesn't have to? You can go up to optimization level 1, but when you do, you got to realize now that you've opened up the possibilities of him optimizing things, he may do something smart like throw the call away completely. So you may not see what you expect to see. Let's go up to a further optimization level. There's 2 and 3, more and more optimizations. Right? See if it changed it at all. I don't know why I need to type that. I got it up here. Okay, so this still looks completely identical. We still had our volatile thing, right? And now we get down to the main. It pretty much looks exactly the same, so I don't see any further optimizations that he did. in this case, right? Anybody see anything that looks different? Well, it's slightly different, I think. He's making a bigger activation record. Before he had 8 here, I think. Now he's got 24. Oh, that may be before we declare those variables I'm thinking about. Yeah. Okay. So I have a question for you. We have local variables in main. We have this R guy, right? And we figured out that one of them suckers is 24 big, right? And we have no other local variables in main. So look at what he's subtracting from the RSP to create space to hold the local variables of the main function. Subtracting 24, right? But there's actually a little bit more to that story that is showing up. The reason he could use 24 is because 24 plus 8 is 32, which is divisible by 8. So to see what nonsense I'm talking about, let's do int x, assign the value 47, and save that. Let's do our thing and see if he changed it. No, he didn't change it. Didn't do anything with that X. He optimized it away. So let me make him volatile so he won't optimize it away. If I could spell volatile. Now, he still didn't do it because I didn't do anything with it. He's still optimizing it away. Okay, let's make some other guys in here. Y. He's still going to optimize it away, I think. Yeah, he's still optimizing it away. Not even doing any of this stuff to do these assignments. So now let's see if we make that one volatile. If he'll leave it alone. Still not doing anything. So I'm going to have to force him to not optimize it away by passing it to a function or something. So int function ug, and I want to pass in an int. Pass in that. Let me pass in the address of an int. Call it a, and then in my function, I will say return splat a plus plus. Just to make sure. Okay, and then down here, I'll use the result. The address of y I'll see if we punched him in the face enough to actually emit the code. Warning, passing argument discards volatile qualification. Yeah, I understand that. We'll get rid of those. Expected semicolon before the thing in line 23. Line 23. Oh, excuse me, all to hell. No, it's not that one. That's not what he's worried about. He's worried about the one up there. Yeah. Okay. Yeah. Okay. That's the one he's worried about. So now we got the deal, and we can look at the code, and we come down to main. And damn it, he's still got 24. How is he passing the stuff? Is he even calling ugh? I don't even see him calling ugh. He's optimized it away. Well, I was trying to illustrate a point to you, but I can't seem to force him to make space for these other local variables. The size that he reserves activation frame must be such that when you do a call to some other function and it plops the return address, which is 8 bytes on the 64-bit machine, that we must be able to guarantee that the beginning of the next guy, the guy we called, his activation frame starts on some address that's divisible by 8, so that all the variables we lay out in his activation record can conform to alignment constraints. So 24 just happens to coincide with something that when you add 8 to it is divisible by 8. So I was trying to make him make something a little bigger and show you that he would have been reserving more space, but I haven't done something over here to make it force him to actually make the call. He's optimizing it away. We could come in here and not do the optimization, right? Then we'd probably see him do the thing, but we get all this other extraneous crud code. So now look at the subtract. It says 48, right? For the activation record. Why 48? Well, he's actually doing the call and he's doing all this crud over here to save these variables. So he needs a bigger activation frame. So he went over the boundary, right? He had to go up to the next size. 48 plus 8 is what? Well, 48 is divisible by 8 itself, but so is 56, right? So when you plop the return address on the stack for the call, we know that the next guy's activation record is on an address divisible by 8. So the point is, these sizes that you see for these activation records sometimes may look bigger than what you think they need to be, right? But that's because he's playing this game where whatever he makes it, if you add 8 to it, that's got to be divisible by 8, right? So you'll see these are always something that's divisible by 8. And that's the reason for that. That's what I was trying to explain, right? Long way to get there. So there's alignment constraint shows up in that respect too, because the activation record where the top of the stack is for the guy that's being called, we're going to plop things for his local variables in there. And in order to make sure those local variables conform to the activation, to the alignment constraints, the biggest one is 8, right? You have to make sure that the activation record starts at something divisible by 8. Any questions about all this craziness? So it's instructive to play around with C code, compile it, look at the assembly language, figure out what's going on. But it's tricky because, compiler will optimize some things away. And if you do the one without any optimization, dead code where he's doing nonsense like this, in the thing where he's saving off the thing into the stack needlessly, right? And that's because you would do that if you were going to call some other function, because you'd have to reuse the RDI to pass the parameter to him. So you'd have to save your parameter off if you needed to use it after you got back from that call. So it does not doing any of these optimizations, right? It's doing all this sort of belt and suspenders dumb code when you have no optimization on. So that can be confusing. Why is he bothering to do all that crap that he doesn't need to do? But as soon as you turn the optimization on, you may get rid of that nonsensical looking silly stuff, but he may optimize some other stuff out of existence, out from under you, and confuse you. So anyways, play around with it and have fun. Any questions about anything? So you got a test coming up that you need to take if you haven't taken it already. And office hours are at 2 today. We can go over any of this stuff from the first 3 chapters you want to touch up on. So the test turns into a pumpkin and disappears at 11:59 tomorrow morning. So make sure you get everything submitted before then. And don't forget to submit your homework by 5:30 this evening. And when you finish your homework, next week's homework will show up. You'll have your project due next week. So we pretty much keep 3 balls in the air at all times in this course of things that you're working on. Okay. Any questions about anything? Well, good luck on your test. And just slowly, methodically work through it using these ideas that we've learned. You'll need a bunch of scratch paper to work out the things, like these sizes of the structs and where are the offsets and all that. It would be good to have a bunch of scratch paper and stuff. Draw some pictures of things for yourself. But roughly 2 minutes per question, and 2 minutes is a good long amount of time. So don't feel overly rushed, but don't dawdle either. Try to keep track of your time and how many you've answered, and use a rough guess of 2 minutes per question is what I should be churning out, to keep pace with getting them all done. You run into a really tough one, make a note on your scratch paper, skip it, come back to it. Do the ones that you can do quickly first, leave your time for the hard ones later. Basic test management strategies. All right. Well, if there are no questions, then good luck on that. And I will see you at office hours at 2, or I'll see you Monday morning. And if I don't see you till then, have a great weekend. It looks like a pretty day out there. What a hell of a day to take a test. The sun's actually out. See you guys later. Bye-bye.